I'm very pleased to be here. So today I will totally change the subject, and I will present a methodology and application of this methodology to the estimation of how fine sediments, of the evolution of fine sediments on gravel bars in a gravel bed river. And this is an image-based method. This work was done with colleagues, and especially Junjun Deng during his PhD. So a bit of context. As you know, anthropic activities are present in the bed of rivers, such as channelization, dams, and dike constructions, water diversions, and sediment mining, and so on. And these activities have an impact of the morphology of river. And in our French alpine rivers, we've seen the evolution from braided system to alternate bar systems often. And the active channel had narrowed a lot. So why am I talking about fine sediment today? It's because there are a lot of interactions between this fine sediment and the morphology. Because when fine sediments, when there are huge fine sediment deposits on gravel bars, then these bars are stabilizing, and vegetation settles in these bars, which, as a vicious circle, reinforces the bar stabilization. And then the flow goes in the main channel, and there is erosion in the main channel, so the bar are rising compared to the main channel, and this reinforces the stabilization. And as a result, there is an increased flood risk due to these rising bars. So the general objective of this presentation is to show if we can understand the dynamics of fine sediment on bars in this context of highly engineered alpine river. And precisely how can we observe and quantify this evolution of fine sediment? Can we measure surface deposits through image analysis? Because as you have understood, I will talk about image analysis. And can this temporal evolution be monitored over time? And hopefully, can we give explanations to these observed evolution? So my presentation will be divided into two parts. First, the image-based methodology, I present the data, the methodology itself, and how we would validate it, and some elements of discussion. And then I will show you how we monitored the evolution over a 2-year time series with application of this methodology, and then the influence of both hydrological and meteorological events. So first, part one, how to estimate fine sediments on gravel bars. Of course, we can go to the field and make measurements, but it's rather time consuming, so we will not have a lot of data, or they will be sparse, both spatially and temporally. We can also use, if we've got one, a calibrated hydrosedimentary model, but it's sometimes difficult to have one which is precise enough to give the estimation of fine deposits. And for a few decades, image-based methods have been used. There are roughly two big families of image-based methods. Either your image resolution is finer than the size of the grains you want to measure, then you use grain delineation methods, such as it's shown on the top picture. If it's in the other case, when the pixel size is larger than the grain you want to know, you switch to texture analysis methods, and many were developed in the literature. So what is the data we have for this project? A time-lapse camera was installed on the bank of a river. It's a river arc in the French Alps. You can see the river catchment. The river flows from east to west, and the study site was selected on the bar, which had been studied in the years that preceded. So the study site is the star, and it's downstream 3 dams the brown rectangles on the catchment figure. So this camera was installed on a tree trunk on top of a bar to have a better viewing angle. And on the right, you can see the type of images to try to set up our method and evaluate it. We also made ground truth images, so close range images taken from someone, and we analyzed them with Bayesian software to get our ground truth data. And then we also made used the Wallman pebble count method on different patches with diverse sediment distribution over the gravel bar. I'm not going to go in the details of the method, but the main steps are here. First, we compute the orthorectified image, then turn it to a grayscale image, and then there are two main steps. First is the high-pass filter. Why do we use a high-pass filter? Is because we have observed that wet sediments near the channel appear darker than dry sediments. So to avoid these image differences, we use this high-pass filter, which will suppress the low-frequency spatial variations, and this is one of them. Afterwards, the next step is the classification. We use the K-means clustering. It's an unsupervised classification method into K classes. And when we looked at the results, the first class resulting from the K-means clustering is only fine sediments. So we were quite happy with that. But when looking closer to the results, in fact, we didn't get all our fine sediments. So some fine sediments were also in the other classes. So we added these classes with weighting parameters. And we conducted the calibration of these weighting parameters with our base grain ground truth data. As a result, the best calibration we got was for K equals to 4, and the coefficient is we take 1% of the first class, 50% the second class, and 10% of the third class, and nothing more. And so we've got our calibrated method. The method is called DEFI, which is French for challenge. So now we wanted to validate our method, and we used the Wallman pebble count results to do so. As you can see in the bottom graph, our results were in good agreement with the Wallman pebble count results, except from one patch, the red one at the top of the image there. We tried to find out why it didn't work for this one. Two reasons for that. In this patch, there were more coarse particles, and Wallman method has a bias for coarser particles, so maybe it's an explanation. The other is that this patch is far away from the camera, so maybe the sampling during the orthorectification step make the image more fuzzy in this area. Then we wanted to know if the method can be applied to different image resolution. So we had one drone image, 1 centimeter drone image over the bar. So we compared the result of this drone image to our bank time-lapse camera. And we also sampled the drone image, which was 1 centimeter resolution, to other images. We undersampled it to 3, 5, 10, 15, and 20 centimeters to see if the resolution had an impact on our results. And what we got is that if the resolution stays between 1 and 10 centimeters, the results, as you can see on the graph, are quite similar to the bank photograph. However, if the resolution goes greater than that, our 15 and 20 centimeters case, then the results are poorer. So we can conclude that our method can be applied within the range from 1 to 10 centimeters. We also wanted to see if the method was robust to different lighting conditions, because in the field sometimes there is sun, sometimes clouds, or even fog. So can the method be robust to these lighting changes? And the result we got is that for this bar portion, the fine sediment aerial proportion was 75%, and it was really stable even with changing of lighting conditions. And the standard deviation, the total standard deviation, was only 2.7%. And if we compare it to to other techniques from the literature, and we took 2 of them, we see that their standard deviation is much greater within each category and in inter-category comparison. So we were quite happy with that. But we also found that our method gave larger surface than other methods. So we wanted to know why. The conclusion was that, in fact, since our method was calibrated with close-range images, we were able to find fine sediments in the interstices between coarser grains, and maybe the other methods do not. And if we apply a median filter to our results, median filter will remove small and sparse isolated fine sediment patches, then we got results that look like the other method. So yeah, it seems that our method finds the fine sediments in gravel interstices. Okay, so if I want to summarize the result we got with this new method that we set up, calibrated, and validated, we've got very good results for a pixel size between 1 and 10 centimeters, and our results are very robust to lighting changes. And this was these results were published in a paper 2 years ago. And now, can we apply this to a long time image series? So the study site was the same, and now we took 1,730 images acquired in 2018-2019, and we also took meteorology and hydrology and sediment concentration data from a close-by station over these 2 years. And these are the results of the method. So we divided the bars into 2 zones. Why? Because one, the red zone, which we called it the marginal zone, was sometimes submerged during high flows. So as you can see in the blue series, there are some interruptions there because of course this bar portion was underwater, so we couldn't estimate the surface. And however, for the high zone the sequence is continuous. What can we see in these results? We can see sharp decreases during late winters, a trend to increase during spring. There is a trend to decrease during summer and fall, and increasing during winter. And there is also a decreasing trend in 2019, but this is partially due to vegetation growth, and I will not speak about that today. So how can you explain these evolutions? Are there links with hydrological events? If you look at the hydrograph, you can see that there are sharp increases here, and they correspond to flood events and dam flush events. It's not because we have a dam flush event that we know the evolution, because if I compare these 2 flushes, 2018-2019, I can see by the result that the evolution of fine deposits is not the same at all. And we concluded that, in fact, the behavior of the evolution depends on hydrosedimentary conditions in the river and on the bar, the initial conditions, and that may yield different fine sediment deposits. To understand what happens, we built semi-empiric model, and we evaluated the flux, the vertical flux of sediments, which we consider proportional to the difference between the concentration and the an equilibrium concentration in the water. It's the Krohn-Partenides law, and we added a term to take lateral erosion into account. This lateral erosion that occurs during the falling limb of the hydrograph. And this was applied to, we considered 5 sediment classes, 4 in sands and 1 in very fine sediments, and this semi-empiric model was calibrated based on data of a previous flush event. So we selected 28 events, flood events, with discharge above 55 cubic meter per second, and we discarded floods when there was also a meteorologic event, to be sure that it's only the hydrology that causes the evolution. There are alternating phases: high flow, the bar is submerged, there is a high sediment concentration, and then the falling leaves, and there is erosion that occurs. It's what explained in the graph there. And if you see the bottom graph with the dashed line, there are two values with this lateral erosion term we added, and we see that the results are quite sensitive to this term. If we consider all the 28 events, what can be seen? When discharge is superior to 90 cubic meter per second, oh, there is per second missing here, the bar is totally submerged, and the dynamics is well estimated by this very simple model. For events with lower discharge, however, there are some very local processes that are not taken into account in our simple model. So sometimes there is erosion in the image data, and the model says it's deposition. So the model doesn't fit very well with the red points. Even if we consider all these flush events, we have some evolution in the sequence that are not explained. In the black circles, you see sharp decreases of the sediment surface. However, there is nothing in the hydrology. So what happens? And that's why we added the meteorological data. Here, the blue bars are the precipitation, and the red triangles are valley breeze events, strong winds, and the wind velocity is the blue dots. And we can see that during these two decreases, nothing really happens with the precipitation. However, there was a strong wind, a strong valley breeze. So the hypothesis is that wind is responsible for this surface loss. So we analyzed the wind data. We've got daily wind velocity evolution. As you can see, the wind is always strong around noon, and it's stronger in April, and it's very low in winter. And we also get the compass rose to indicate the direction and the frequency of this direction. And we can see that the wind is aligned with the valley. So what happens when wind blows very, very strong? You can see in this wind event that the sediment surface decreased with, I didn't put the data, but there is a strong decrease of the sediment surface. But for an event with quite the same wind velocity, 12 meters per second, well, nothing happened. So what is the difference between these two events? First is the quantity of sediments, but most importantly is the initial moisture of this sediment. In the first event, sediments were dry, and the second one, they were wet. So wind has a significant impact on sediment transport on the surface, but only with dry sediments. We try to explain that with a simple wind transport model from Horikawa, and we added a term to take this moisture change into account, and we considered that the sediment were wet if precipitation occurred during the 5 day, one of the previous 5 days, and they are dry if there is no precipitation during this 5-day period. And the results, the comparison with the model, are that for the 4 events with initially wet sediments, there is a good correlation for the high zone with observed surface decrease of sediment surface. So this is the link with the wind transport. In the marginal zone, however, we see the opposite. So surface increases when wind blows, and we think that fine sediments that are transported from the high zone are then trapped in the marginal zone, because marginal zone is close to the channel, so it's always wet, even if it's not raining. So, brief conclusion to my talk. We were able to develop a methodology, an image-based methodology to measure sediment deposits, fine sediment deposits on the surface, and we were able to evaluate the evolution of this surface sediment over a long time series. We made links between these evolutions and hydrological events, but these links are complicated because the evolution depends on the hydrograph, on the sedigraph, on the initial state of the surface. We were able to predict this evolution from a very simple semi-empiric model when the bar is fully submerged. We also showed that there is a strong effect of wind during strong valley breezes events, with a decrease of deposit surfaces when the sediments are dry. And we also published a paper for these conclusions. However, there are limitations to our methods. First, that my conclusions are limited to what happens in the surface of the bar. But fine sediments are not only on the surface, they are also infiltrated and within the matrix. So what are the links with the matrix? This is still an open question. We also plan to apply this method to other bars, other rivers with different type of sediments. Are the results still valid? And this will be done this year. And with this work, we want to come up with proposals to improve river management. Since these fine sediments, and we know how to measure these fine sediments now, they are very important for bar stabilization. We want river managers, to take that into account when they decide how they make their dam flushes, for instance, in order to reduce these deposits and to keep rivers in a better ecological quality. So, thank you for your attention.
Any questions?
Interesting part you just presented. Because this is what it happens more or less in foothills. But when you come to the floodplain regions, will not have that much of mixing. You will have either fine particles, only fine particles will be gradients, but in foothills you will have the gravel as well as the fine particles. So that way, quite interesting to know how the bar or evolution is happening, and with a very low cost image processing. Yeah. It's not any hi-fi equipment putting in the river, just doing the image processing, the data. And you also showed that you tested that thing with a drone data, with the different resolutions. So that's quite interesting for us to know, to go to that level to look it. I also agree with you that 2 years data is too limited to understand cause behind it.
Yeah.
So because bar evaluations and the 2 years data, it's a too limited data set to really establish between the cause and the
you're right. And one thing that was quite time consuming, in fact, in analyzing all these images, is that we put our camera on a tree trunk, and it's not a big tree, but it's quite a tree. But we were surprised that the camera moves, and it moves a lot when the wind blows. So we had to modify the geometry of the camera for each image, in fact. And our automatic tool didn't work well with that. So we had to do it manually. And it's our PhD student, Junjin. He spent a lot of time doing that. But of course, we could add more data to have a longer series. It would be interesting to have different. There were no significant floods during this 2-year period, so maybe with higher floods or different meteorological, hydrological configuration would be very, very useful. Yes, I agree.
But then it's really interesting to see the role of erosion process on the fluvial system. And so my question is related to that the role is limited to the redistribution of the fine sediment of the bar surface, or erosions are also bringing sediment from hill slopes and depositing?
We don't really know that. So there might be some other sediment coming, but we were not able to measure that with this system. But maybe Margot has an answer.
Yes, maybe good idea.
Long live India and France friendship.